All right, hello everyone, and welcome to another AP Chem video. Today we are going to be covering Unit 1, Topic 2. So, one of the objectives of this unit, in addition to revisiting moles and molar mass, is to explain the relationship between a mass spectrum and the isotopes of an element. Okay. The topic objectives for today is to look at a mass spectrum and be able to determine the identity and the relative abundance of isotopes of any particular element. And then finally, use any information that you can from a mass spectrum to calculate the average atomic mass of an element, okay? Knowing that it's a weighted average of the isotopic masses. All right, so quick little review. All right, isotopes are atoms of an element with a different number of what? Okay, that is neutrons. Okay, because if you remember from your previous chemistry class, the three I's, protons are the identity, electrons are ions, and neutrons are isotopes. Okay. Now, there are a couple of ways of communicating or writing isotopes. Okay. Probably the most common way that you're going to see is this one, okay, where you have the element symbol followed by the atomic mass of that isotope. Okay. And for the example that we're looking at now, uranium, it can be either uranium-235 or uranium-238. Okay. Those are the more common ones. Actually, 235 is the one that's used in nuclear reactors. Okay. Now, if we're looking at it from the perspective of atomic symbols, okay, we have the element symbol, all right, followed by the atomic mass in the upper left. And you might be wondering, where is the atomic number? That's usually not included just because that number doesn't change with the element symbol. So as long as you know the element symbol, scientists and chemists assume that you can figure out that information. All right, so now that we know or remember what isotopes are, let's try and learn a technique that is related to isotopes, and that is mass spectroscopy. Okay, it's a very common analytical technique in chemistry labs that measures the mass to charge ratio of ions. Okay, and you might be thinking, well, ions? I thought we were learning about isotopes. Well, there are isotopes within ions, okay? So before we go into the analysis of mass spectroscopy, I just want to give you a very brief, very elementary understanding of how mass spectroscopy works, okay? So what happens is you inject a sample right here, and it goes into what is called an electron gun or smasher, which is essentially it obliterates the molecules of your sample, okay? And it fragments it into some predictable pieces, okay? Once those have been smashed, they enter the magnet portion of mass spectroscopy. And in here, this is where those fragments will start to separate, okay? And they separate based on the mass and the charge, okay, of those ions, okay? The heavier that a fragment is, it will be attracted closer to this magnet or this side of the tube or whatever, and the lighter ones will kind of hit the other side, okay? Now, if the instrument is calibrated in such a way that a certain fragment with a certain mass to charge ratio will hit the detector just right, okay? Once it hits the detector, that information is relayed to the computer, which will confirm the presence of a certain ion or isotope. So what happens when you subject a sample to mass spectroscopy and it spits out the information onto a computer. Okay. Well, what you'll typically see is what is called a mass spectrum, and that is showing you the information from your sample. Okay. And it's plotted relative to the ratio of ions, or sorry, the mass charge ratio of ions relative to the abundance. Okay. So on the x-axis, you'll see this m/z, okay? And on the y-axis, you'll see relative abundance, okay? mz is simply the mass of the fragment divided by its charge, which is why you often hear it called mass to charge ratio, okay? Sometimes you'll see it as m/e or mass number, okay? Here is an example of a mass spectrum of just chlorine, okay? Here is the mass to charge ratios, or simply the atomic masses, and the relative abundance of those two isotopes. Okay. Now, as you can see, chlorine really only has two isotopes, and their relative abundances are about 75 and 25%. Okay. From this information, we can actually calculate the average weighted atomic mass of chlorine. Okay. And because the isotopes and their relative abundance are always consistent, you would always see this 3-to-1 ratio in a mass spectrum for chlorine. So let's calculate the average atomic mass. Okay? Because we only see two peaks, we know there's only two isotopes. Those are chlorine-35 and chlorine-37. Okay? The fractional abundance at this point is kind of a guesstimate around 0.75 and 0.25. Now, to calculate the average atomic mass, or the weighted average atomic mass, we're going to multiply the mass of each isotope by its fractional abundance to get its isotopic contribution. Okay? And the more abundant an isotope is, the more it will contribute to the average weighted atomic mass. Okay? From here, what we're going to do is we're going to add these numbers up, and we get the weighted average atomic mass to be 35.50, which is pretty close to what you see on the periodic table, give or take 100th or 1,000th decimal place. All right. As I mentioned earlier, given a mass spectrum, you should be able to identify an element. Okay? So looking at this mass spectrum and the information that you were given, what element do you think is being portrayed? So pause the video and answer the question. Okay. If you look at the two peaks, you'll know that they are at 79 and 81. Okay. The relative heights tell us that they are about 50% each. Okay, so 50% of isotope 79 and 50% of isotope 81. Which means if you were to take a weighted average, you would probably see average weighted atomic mass of around 80, okay, which is what we're going to use to identify the element. So if we looked at the periodic table, you would scan the average atomic masses, and you would get to a point where you got to bromine, because bromine has an atomic mass of 79.9, which is pretty close to right in the middle of the spectrum. So the answer to this question is bromine. All right, so the last portion of this video is to predict what a mass spectrum would look like based on given certain isotopes. The example that we're going to look at is lithium. Suppose lithium shows up in two isotopes, lithium-6 and lithium-8. What would the mass spectrum look like? You might be thinking, how the heck were you supposed to do this? Well, the one piece of information that we're going to use is the average weighted atomic mass of lithium that is shown on the periodic table, which is about 6.9. Now, in order to predict the mass spectrum, we need to know its relative abundance of the isotopes, okay, which you might find familiar to something that we did in a previous chemistry class. Okay? So we are solving for the fractional abundance. So we have assigned one variable to one isotope and another expression relative to that variable for the other isotope. And because those fractional abundances should add up to 100%, or fractional abundance, it should add up to 1. Okay. So we're going to multiply the mass of each isotope by its fractional abundance, and we get the following terms. And we know that the sum of these should add up to 6.9, which means we're going to have to do a little bit of algebra. Okay? So we're going to solve for the variable y, which will give us our fractional abundance of lithium-6, which in this case is 0.55. Now, if we were to convert that to a percent, it would be 55%. To solve for the other fractional abundance of my other isotope, I simply just take the difference and I get 0.45. If we go back to our mass spectrum, okay, this is relative to percent, so we need to multiply it by 100, so we get 55 and 45% respectively. Okay. So to end this lesson, predict the mass spectrum for isotopes gallium-68 and gallium-71. Okay. We'll go over the answers in class. Thank you for your attention today.